Okay, it's about 20 past and I'm going to make a start. Okay. So those of you who have been paying close attention to these slides and the content will see this is actually labeled as an Archer course. Running a GPU course under the ambit of ARCHER, which is the UK National Research Computing Facility, was always slightly odd in that ARCHER never had any GPUs, but we've recently acquired a new system which does have a significant GPU facility, which is Cirrus, and that Cirrus machine is the one we will be using for the exercises today, tomorrow, and on Thursday. As I said, my name is Kevin Stratford. I work at this entity, Edinburgh Parallel Computing Centre, which is at the University of Edinburgh, and also doing some of the lectures over the next couple of days. We've got Rupert Nash. Our emails are there if you want to email us. So these slides are reveal slides, and they are served up from the course Git repository, the address of which is there. So if you want to follow the slides at your own pace, rather than watching me flick through them, you can go to
link to that
address at the bottom there and follow at your own pace. So in the Git repository as well are the exercises and the instructions for the exercises, which we'll need later on. All this stuff has a license. As I say, Archer which was, still is, the UK National Computing Facility, looks like that. Cirrus is another bunch of boxes which look, in some sense, rather similar. These all actually sit in a data center which is somewhere to the south of Edinburgh, and to add to my nerves, they are doing some electrical work at the data center today, so the system is at risk. So if they pull the wrong plug out, the whole thing will go up in smoke, and we will have to make a contingency. So here's the timetable for the first day. The first lecture, what I would like to do is just to spend some time thinking about the differences between GPU and more traditional CPU computing, and how the architectures of these different machines differ, and how that affects the way in which we may think about programming these machines. Most of the course we have couched in CUDA as a programming model. I don't particularly want to get too hung up on one programming model versus another. We'll have some examples of some other programming models tomorrow, but CUDA is probably the most widespread and perhaps the easiest to get going with for a course of this type. Perhaps what is more important are the sort of principles and the concepts behind the programming, which really carry over to all the different programming models. So there's the timetable for tomorrow, which is similar to that in terms of the schedule to today. And day 3, which is Thursday, again, we'll start this hackathon. So the idea here is that you can either have a little more time to try 1 or 2 of the more difficult exercises, or have a look at your own code perhaps, but we also have a mini app which we can supply if you just want to have a go at a slightly larger problem. We have 2 NVIDIA staffers available also on Thursday, who will be available to answer your questions. And to formalize that, Alan Gray of NVIDIA will give a lecture at 10:10 on Thursday, looking at new features in CUDA 11. At this point in the talk, I usually have to talk about local information. I should say I am being in the office. If there is a fire alarm, I will have to evacuate, which will leave everybody else in limbo. So
don't worry, I'll take over.
That's just Rupert will carry on seamlessly.
While Kevin burns, yes.
Okay, so and there's some details of the exercises there. Okay, so if there are no, so if you haven't seen these reveal slides before, you can click on the blue things that are links, which you click on in the normal way, and you use your right arrow to cycle through the slides and left arrow to go backwards. So I'll start, if there are no questions, I'll take a look at the first lecture, which is this one on GPU concepts. If you do have a question as we go along, probably the best bet is to type it into the chat, and one of my colleagues will pick it up and we'll do our best to answer. Okay, so this first lecture, we're going to have a bit of a think about basically how computers work, and in specifically what the differences are between GPU and CPU computing. And as this is scientific computing, we are particularly interested in factors which influence performance. And so how do these factors affect performance in both CPU and GPU picture? And how trends in the development of architecture are affecting scientific programming, and how one goes about the business of scientific programming for applications. As we said in the description of this course, this is intended at application programmers. I'm not really going to say anything whatsoever about subjects such as machine learning and so on. So if we take a very simple picture, which is seen here on the left, of a computer, we can think of it as a processor which is attached to some memory. And in thinking about the performance of this setup, we've identified here 4 issues which you might think about. The first is typically the clock speed of the processor, the rate at which the processor is able to issue and execute instructions. But there's then also the issue of moving data in and out of memory. So there are two different strands to this. The first, which is point 2, is memory latency. So if I am sitting on the processor and I ask for a new piece of data from memory, there is a latency, there is a time cost to go out to memory at all and retrieve a piece of data. If I can do that at all and I need a lot of data, one may then ask about memory bandwidth. That is, how much data I can push between memory and the processor in unit time. So that's usually typically expressed in something like gigabytes per second. The fourth point here is one of parallelism. So if a basic unit looks something like that on the left, to what extent can I replicate this picture and improve time to solution by dividing my work between different units of computation. So that's the basic essence of parallel computing. So we just a little look at each of those 4 points in turn. Historically, those of you who may remember previous decades, the headline in computing speed was always clock speed. If you wanted a faster computer, you bought a processor with a faster clock speed. Because of fundamental engineering limits, basically related to power consumption, increases in clock speed are no longer really possible because clock speed goes up and you have to reduce the voltage, and you need a finite voltage to represent your bits as 1 and 0s. So that these fundamental engineering constraints have really meant that clock speeds are not really significantly increasing any further, and that's really the sort of traditional Moore's law picture, if you like. Although that is not quite exactly what Gordon Moore was originally talking about when he made his famous law. But this picture, which is missing a label on the vertical axis, which I think should be megahertz, shows pretty clearly that there was a rapid increase in processor clock frequency from about 1970 up to about perhaps 2005. That really hit a ceiling at that point, and clock frequency increases are no longer really available. If you are okay with your color vision, the other thing to take away from this chart is a rather depressing elimination of competition in the market, which again may be something that is just slightly beginning to change again in the most recent years. So here's the second performance factor we wanted to think about. This is this one of memory latency, and this is really a serious concern in processor design. It can cost you of order 100 or even of order 1,000 clock cycles to retrieve data from main memory. So if you're on the processor and you have to stall for 100 or 1,000 clock cycles doing nothing while data is coming back from main memory, that's a real problem, a real inefficiency. So a great deal of processor design has gone into reducing the potential of being affected by this issue of memory latency. And this really expresses itself most commonly in cache hierarchies. So the idea here is you have basically smaller amounts of memory which are in some sense closer to the processor and therefore take less time to get to, and you hope to reduce this memory latency problem. So this costs you a certain amount of complexity in hardware design. You need all these caches and you need hardware to control these things, and you need coherency mechanisms to make sure you agree which data are up to date in these different cache levels and so forth. There are also other latency hiding measures done in hardware. Some of you may have come across hardware multi-threading, which in Intel land is referred to as hyper-threading. This again is really a measure taken so that if one thread of execution encounters a long latency operation asking for memory, another thread of execution can come in and do some useful work while you're waiting. And there are other measures such as out of order execution of instructions, all really coming from this need to get around this memory latency problem. So just as a sort of visual picture of that issue, here's a picture of an Intel Sandy Bridge die. We don't particularly care what it is. It's just as an example. So what is to be taken away from this is that our processing, which is actually done on the processing cores, we can see 6 of them here, and there were probably, I suspect, the 2 blank boxes on the left and right below the last core are cores which have been marked out in the manufacturing processes. But as I say, the point to take away, in the middle here we have this huge area devoted to cache memory and memory controllers. So that's just a picture in sheer physical real estate, the amount of effort that is going into cache memory and getting around this memory latency issue. So the third point we mentioned is memory bandwidth. CPUs generally use a commodity, what's generally termed double data rate, random access memory. Doesn't really say what double is relative to, but in some sense gives you a memory bandwidth which for a general purpose commodity machine is acceptable. For scientific computing, in practice, memory bandwidth is often very important in limiting how fast real applications perform. So particularly if you're in areas such as fluid dynamics, you'll almost certainly be bandwidth limited, and you probably don't really care so much about processor performance in terms of clock speed. And our fourth issue was that of parallelism. Again, in recent years, the source of increased performance for many commodity items is now to use more cores. So your washing machine at home will probably now have a multi-core processor in it. Your mobile phone will probably be a multi-core thing, and this again is to add parallelism to provide more work rather than increasing clock speed, and thereby you keep power consumption manageable. Here's another example. This is a many-core chip. This is the late unlamented Intel Knights Landing. So you may be able to see the smallish squares you can, or roughly squares here are the cores. I think there are about 72 of them on this die. Compared with that previous picture, you may have the feeling that slightly more real estate is being allocated to cores here, and slightly more to computing than in that previous picture. So that's more or less the traditional CPU picture. So this is and cannot be denied that this is a highly successful design for commodity products which do general purpose computing. They're used for everything from operating systems, databases, web services, web servers, everything just about you could mention can be done with these machines. And there are inevitably design compromises which go into these commodity items, which means they may not specifically lend themselves to high performance computing in the scientific sense. So much of the functionality you may need on one of these commodity processors you may not care so much about in high performance computing scientific application. And so, in some sense, you have wasted real estate, or in the end, money in these features, which you don't really need for, or need only infrequently for high-performance computing. However, this is a huge commercial market, and in the end, commercial concerns are real and undeniable and inevitable. So while in the past there have been some great designs of hardware specifically for scientific computing, there was never really an economic model behind them, and so they were ultimately not a success. So the services you use for scientific computing are almost always commodity-based ones. So in the end, it is a lesson from the dismal science of economics that what we have to do as scientific programmers is really strongly affected by economic questions. At the same time, historically, there has been a different strand of computing going on in parallel, if I may use the phrase, which does have a very strong economic rationale. And this is the issue of graphical processing units, and there is a huge and lucrative market for games which require graphical processing units to render images, which is the main business of, or one of the main businesses of games. Historically, there have been two dominant manufacturers in this area, AMD and NVIDIA, who design GPUs specifically for the purpose of doing graphics rendering. This problem is an embarrassingly parallel one, in that every pixel on your screen can be worked on independently to render a whole image, potentially. So there's a long history of thinking about parallelism in GPU computing, and it also turns out the rendering problem favors a reasonable balance between floating point performance for doing actual computation and memory bandwidth for moving data in and out. And it turns out that that balance is often a good thing to have for scientific applications. So the next few slides, we're just going to have a think about these four factors that we were thinking about for GPU computing. Historically, GPUs have used relatively modest clock speeds. The most recent models have tended to catch up with the GPUs on this point here. But again, the route to performance for GPUs was always based around the idea of parallelism, which we'll see later on. So the problem of memory latency, it's still a problem. It has not gone away, but the strategy taken by the GPU design to try to hide this problem of memory latency is again related to having a very large degree of parallelism. So the basic idea of GPU computing is to schedule very many, and I can't stress this enough, if there's one thing to be taken away from this course, is you need very many parallel independent tasks to perform, potentially more than can be accommodated on your hardware at any one time. If we have these very many independent tasks, we can arrange it so that if one task encounters one of these long latency operations, we can very quickly swap it out and schedule another task which is ready to do some useful work. And this is the basic design principle which is implemented in hardware to be very fast, that allows effective parallel performance on GPU computing. So you may think of it as the multi-threading idea writ very large. Here's the picture for memory bandwidth. This picture comes from NVIDIA, so may be taken with some care. So the left panel is flops, maximum performance. Perhaps more interesting is the right panel, which is peak memory bandwidth. And even given some caution that this is an NVIDIA picture, we can see here that on the right, that the increase in peak memory bandwidth on the CPU is really rather flat compared with that which has taken place in the GPUs. And this is really a design decision to do this and a cost decision, but to maintain the balance of memory bandwidth and compute, the GPUs have relatively much more memory bandwidth. So the fourth point in performance is the idea of parallelism. So GPUs have, again, relatively speaking, a large number of cores. In NVIDIA jargon, the basic unit of GPU hardware is often referred to as a streaming multiprocessor, or SM, of which there is a sort of schematic picture here. You can see that there are a large number of cores, and there are some double precision units and some load store units and some special function units there as well as various bits of memory related stuff. So this is the basic unit, and these units are replicated to a large degree to give you a lot of parallelism. like so. So the many of these streaming multiprocessors, or SMs, are put together in the CUDA or NVIDIA jargon as a graphics processing cluster, I think, which looks schematically a bit like that. So in terms of the sort of trends in the coming years, while in the past these things have been really separate concerns, perhaps in the future CPUs and GPUs will become more integrated. So, for example, from the programming point of view, one of the things that we will see is an issue for writing our applications is that the GPU and the CPU may want to look at a different memory space, which can complicate matters, but in the future these memory spaces will probably become more uniform. But what is not in doubt is the need for parallelism in this picture. Okay, so how does this hardware picture relate to what we would actually think about in terms of programming, or what we would do in terms of a programming model for a scientific application? So GPUs being designed for graphics rendering historically relied on graphics specific languages to do their work. There were things such as DirectX and OpenGL. And while there were one or two early, what might be called heroic efforts to program scientific applications in things like DirectX, this was not really a practical option for very many people. However, in about 2007, NVIDIA developed an API, which is CUDA, which stands for Compute Unified Device Architecture. And NVIDIA really introduced this primarily for their business, to make the business of graphics processing easier. It just so happened that as a byproduct, it also became much easier to start thinking about programming scientific applications in CUDA. And so the first scientific applications really started appearing at about that time in CUDA. At the same time, there was a separate development, OpenCL, Open Compute Language, particularly important in the mobile phone arena, was developed. It's not perhaps had so much traction in scientific applications, although there are applications that do use it. Perhaps a little more heavyweight than CUDA to get started, but we'll see. You can have a look at this tomorrow if you're interested. There are also directives based approaches to GPU computing. If you're familiar with OpenMP, you'll know the type of thing that directives means. This means putting in special hints for the compiler to allow the compiler to generate code which will execute on the GPU.
Have we lost Kevin?
Sort of directives
We briefly lost
standard
Kevin. Yeah, I think you
had a
died for a second
schism,
there.
and we had OpenMP, and OpenACC was also created. We'll see again a bit more about this tomorrow. So the situation was a little slow to become clear, but it is now a bit more stable. So the benefit of directives is that they are relatively pain-free and easy to introduce. Although if you want the greatest extent of control, directives are sometimes difficult to interpret in terms of where performance is or is not coming from in your directives approach. I should perhaps say at this point, for anybody doing Fortran, directives are still probably a very good way to go in terms of GPU computing, and there are serious people who do use directives in Fortran applications. So in terms of what type of application a GPU could be useful for, again, I cannot stress this point enough. You must have significant parallelism, usually data parallelism. If you don't have a problem that cannot be decomposed into many independent tasks, you may struggle to find effective use of a GPU. That's just the way it is. It may mean you may have to completely rethink the way you look at your problem and how you approach it, or what algorithm you use. So what one is typically trying to identify in a code which one is thinking about moving to a GPU is a small amount of code which is usually referred to as a kernel, which is where most of your computational effort is going. So if you know most of your computational effort is going into a specific part of the code, then you should target that piece of code to run on the GPU. So there may be problems for which GPUs do not have so much to offer. If you have little parallelism, you may struggle. If you have a lot of I/O, GPUs don't solve that issue. I have nothing much really to say about that. If your code is poorly structured and you can't identify these kernels where most of the computational effort is going, again, you may struggle. There are also some areas where there has been an increase of interest in the last few years when GPUs were first used for scientific applications. They often only had single precision floating point arithmetic, that is 4-byte floating point units, because they were only interested in rendering graphics problems. You don't really care so much. And so when people started doing scientific problems on GPUs, people started demanding we must have double precision 8-byte floating point operations, which duly appeared. But recent interest in the deep learning problem, which again is somewhat fuzzy in that you don't care so much about floating point arithmetic. There has been renewed interest in reduced precision computing, and GPUs now often offer half precision or even quarter precision floating point arithmetic. And there is some interest in some areas about trying to make use of this stuff, because if you can reduce the precision of your arithmetic, i.e. use 4 bytes instead of 8 bytes, that immediately halves the amount of data you have to potentially move around, which is, again, from this memory bandwidth point of view, quite an important consideration. There's been quite a bit of work recently in particularly CUDA on representing problems as graphs and executing graphs, but I'm not going to say, don't think anything too much about that in this course. Okay, so some examples of things that do use GPUs. So if you're a user of basic linear algebra, you'll be familiar with things like BLAS. And so, for example, CUDA have a BLAS implementation for GPUs, so this can be useful. If you've heard of things like PETSI, again for basically linear algebra problems, they have CUDA and OpenCL. I think that's true still, an implementation, and another large package is Trilinos from Sandia, and they used something called Kokkos, which is an abstraction framework in C++, which we'll have a look at tomorrow. A very big area in scientific computing is that of quantum chemistry and molecular dynamics. So here, situation is perhaps a bit more mixed. Again, another big area is CFD, particularly if you're lattice-based CFD. Data parallelism is there. different packages have different mileage in whether they have GPU implementations or not. So, as I said, the elephant in the room, which I am deliberately not saying much about for this course, is big data and machine learning. So the thing that I usually limit myself to saying about this subject is that it so happens that the training problem in machine learning can be expressed as basically a matrix multiplication, and if you want to do matrix multiplication, GPUs are an excellent resource. So that's essentially why there's all this big noise about GPUs and machine learning. A very cost-effective way to do large machine learning problems. Okay, so that's a kind of overview of the sort of background of the hardware picture. So what we're going to try to do in this course is to try and put some of these ideas into actual practice and have a look at some of the ways you can do this with an eye to learning some of the concepts, but also keeping an eye on how one can do this for scientific programming while keeping an eye on issues such as performance, portability, and productivity. That is the ease of writing new code and the ease of development of an application in a given framework. Okay, I'm going to stop there. There's a question in the chat regarding directives-based approaches, and the question is, do we have any convergence between OpenMP and OpenACC? In terms of convergence, I would say no. They are still separate and seem to be taking separate paths. A recommendation for the long term may take some care. It may depend on what you're trying to do and in which language, but certainly if you're in Fortran, one should consider either OpenACC or OpenMP. If you're in C or C++, you have a great deal more choice in what you can do in terms of programming models. So there, the case for directives is less clear-cut. But it should be said, if you just want to experiment quickly with something, to try something out, directives are a very good way forward. But if you're concerned with long-term development, you might want to think about looking elsewhere to get around this issue of what is the standard I should be conforming to. which is, I agree, problematic. Okay, so it's 11:30 and we'll keep going. So if you had this problem with, you followed the link to the slides and you've got so far but no further, you need to click on this blue link, which is timetable and local information. And then this will take you into the introduction, and use the right arrow key to go forward through the slides. And then we can click on the next lecture, which is CUDA programming. Okay, so this is the first time we've done this course online, so I'm not quite sure how the timetable is going to pan out, but we should try to take our time so that people have enough time to have a go at the exercises and so forth. While the timetable may slip a little, we'll try to keep more or less to the published times of breaks and start and end. I should also say at this point, in a physical course, we often try to have a bit of fun by going around the room to ask people to say a little about what they do and why they're interested in GPU programming. I'm not going to do that now, but we might have a go tomorrow. So there's a warning for you. Okay, so the previous lecture was discussing the sort of background to GPU computing. We're now going to go on to look at the detail of how on earth one actually goes about doing this, and then there'll be an exercise at the end which we'll test to see if we can get to grips with it. So the model we're going to use is CUDA. This is NVIDIA's Compute Unified Device architecture. So I'm going to give a little background on the programming model and some of the things we need to think about. I'm going to talk about the issue of blocks and threads and the issue of data management and data movement. So first of all, a bit of jargon. And the jargon we're going to look at is the jargon of host and device in GPU computing. So typically what one finds in a real machine is one doesn't have a GPU sitting on its own. It usually comes coupled to an associated CPU, and so the jargon is to refer to the CPU as the host, and the GPU is often referred referred to as the device. So the CPU is said to host the GPU. So historically, one of the most important things one has to think about in GPU computing is that the CPU, the host, and the GPU, the device, have separate memory and separate memory address spaces. So if one writes a program for a CPU, one can access memory through variable references, and memory you can perform operations on memory in the usual way. In the same style, if you're on the GPU, you can access variables through device memory references alone. However, what you cannot do in general is on the device, say, directly access memory which is sitting on the CPU side. So there is typically some process of copying data between CPU memory and GPU memory, and to get results back out again, one typically needs to think about copying from GPU memory back into CPU memory, where final input-output usually occurs. So the boxes on these diagrams are meant to be meaningful in the sense that the CPU typically has a relatively large amount of memory associated with it. A modern CPU, you may expect to have maybe, I don't know, 128 or perhaps 256 gigabytes of memory. And the arrows there between the CPU and CPU memory are supposed to be representing we have a modest maximum memory bandwidth available. In contrast, for the GPU, the amount of GPU memory is typically relatively small compared with the CPU. So a modern GPU may have memory associated with it of perhaps 16 gigabytes. However, the arrows there are supposed to, between the GPU and the GPU memory, are meant to represent we have a stonking big maximum memory bandwidth available there. So the issue of the copies going from left to right and right to left is potentially a bottleneck where, again, we may have a relatively poor memory bandwidth. This often goes over PCI Express, for example. So that's a bit of the jargon. So the other bit of jargon we should be aware of for this talk, I might fall into the GPU memory here on the device side on the right is sometimes referred to as GPU global memory. So if I fall into the jargon of talking about global memory, I am referring to GPU memory. Okay, so that's the basic picture. So as I said, in terms of the programming model we're going to be thinking about here, which is CUDA, was introduced as an easy alternative to what went before. It started life more as a C interface, but in recent years has become what is really a C++ interface. And so this is split into broadly two parts. There is a part, an API, which is available from the host, that is from the CPU program, which the programmer uses to control activity on the GPU. And then there are these so-called kernels, which is user code, which is executed on the device or the GPU. And the model is a threaded one in CUDA. So that's the basis. As I said, that is essentially a C++ interface. For those of you who may be interested in Fortran, there is an extension to the Fortran standard referred to as CUDA Fortran, which allows you to write code in Fortran, which may be compiled with an appropriate compiler, and the one we will use is NV Fortran to allow you to execute your code on the device. Okay, so here's this hardware picture again. Schematically, we have a picture where we have these streaming multiprocessor with lots of cores and potentially some memory associated with the particular streaming multiprocessor, and we're going to throw lots of these things together to make up a GPU. So the exact numbers of cores and hardware components and so forth obviously depends on exactly what hardware you have. And as a programmer, we do not particularly want to be concerned with exact numbers of cores and so forth in the hardware. So we want an abstraction of the hardware to allow us to write a program in a general way. And the abstraction is couched in terms of threads on in CUDA. Furthermore, what we're going to see is that the problem may be abstracted into what are referred to as blocks, which broadly map onto the streaming multiprocessors, and each block is going to contain a number of threads, which are broadly going to map to be executed on a single core. And as I say, we don't really want to care about the exact details of the hardware. We want to simply describe in our program what you can think of as a grid of blocks and threads, and then the runtime will go away and schedule the work we have described as it sees fit. So just some fundamental background. We're going to be interested in describing, for simplicity here, a two-dimensional problem in a Cartesian picture, or a one-dimensional problem in a Cartesian picture. So these simple containers will crop up quite a lot in CUDA. There is something called a DIM3 structure, which is just an aggregation of an integer x, y, and z, and the Fortran equivalent is a type DIM3, again with these three components. So we'll see these things in what follows. Let's think about an example here. Here I've got a loop expressed in C here of a given length, and for each iteration of the loop I am going to make an assignment to an array which I've called results based on the loop index. And what you will see from that piece of code is that all the loop iterations are independent. So one iteration does not depend on any other iteration. So those of you familiar with parallel programming should then immediately be saying, here I have the potential for parallelism. I can do all those iterations conceptually at the same time because they are independent. So how does this look in CUDA? So this is what one would do in CUDA. So in order to think about executing that loop in parallel on a GPU, one would be interested in writing a C function, which is we will refer to as a kernel, which we would target for execution on the GPU. And CUDA knows that this is a kernel which we target for execution on the GPU by introducing this global double underscore attribute, which is put before the standard C function declaration. So this global double underscore thing is a special CUDA attribute, which is saying this piece of code is something I want to execute on the GPU. And what one sees here is that I have my piece of code. My result for index I is just 2 times the index as before. But we'll see that the loop itself has disappeared, and we have replaced the loop index by this assignment I equals thread index dot x. So this thread capital I dx thread index is one of these DIM3 structures which has a special status in CUDA and it is supplied by the runtime and will take on the value of the appropriate thread, or the appropriate value for each thread that we are going to use to decompose the loop. So we've gone from a picture there where we have an effectively serial iteration through a loop where one iteration is performed after another, to here where we have the same operation which we've declared is going to be executed on the device by this double underscore, global double underscore thing. And somehow we need to identify what is doing the job of the loop index, and this is replaced by this thread index variable, which is supplied by CUDA. Notice I haven't declared this thread index thing anywhere here. So the other thing to note about this CUDA C function is that it must be declared as void. It does not return a value. So okay, how do I go about executing this kernel which I've declared in the previous slide? So what I need to do to recover my loop, which went from 0 up to 1 minus loop length, I need to execute that kernel in such a way that I have the right number of threads, and each thread will perform one iteration of the loop effectively. So this is the way that it's done. So we've declared a couple of these dim3 things. First one is called blocks, and the second one is called threads per block. So as this is a one-dimensional problem, I'm going to declare that I have one block of work in X, and the number of threads per block in the X direction is the loop length. What I then do is I invoke this myKernel function, which is what I declared in the previous slide. That's the name of the kernel. And then there's this special triple left angle bracket, triple right angle bracket notation in CUDA, which indicates that this myKernel function is going to be launched onto the device. And it's going to be launched in such a way that it has one block of that number of threads per block. So those are the arguments inside that triple angle bracket notation, and this is referred to as the execution configuration. My kernel argument, which is this array result, goes in as the arguments at the end in the normal way. Okay, for those of you who might be interested in Fortran, the analogous code will look like this. You declare a subroutine in Fortran, but you put before it this special CUDA Fortran extension, which is this attributes global. to declare that this is a kernel to be executed on the device, and then you get made available to you a special variable thread index, which again is one of these DIM3 things, which you use in the usual way via the component selector in Fortran. And likewise on the host side, you would start this kernel off by executing with a call my kernel function, this special triple angle bracket execution configuration, and the argument there. Okay, so that is potentially limiting in that we've only used one block, which may limit us to the use of one streaming multiprocessor. So we want to typically have very many blocks. So if one wants to use a lot of blocks, one then needs to start to think about splitting up the problem space into blocks, and then a sort of global array index would be computed as a function of where you are in the block picture, and then where you are in the thread picture within each block. So each block may have a number of threads, and we start off a given number of blocks. Then we can use a lot of blocks. So the execution of such a kernel might look like the following, where we've decided we want a certain number of blocks. We then, to make sure we compute the appropriate range of loop indices, should set our threads per block to the total loop length divided by the number of blocks, and that will cover the whole problem range for us. There is an assumption there that the loop length is exactly divisible by the number of blocks in that case. We'll see what happens in the general case later. So that introduces two more of these special DIM3 variables, this block dim, which is the number of blocks in the x direction, which we've set down here, and this block index, which tells us where the current thread is in the block picture combined with the thread index. Okay, likewise in Fortran, the picture is similar, except the one thing to note about Fortran, because Fortran like to count in natural numbers like natural people, indexes typically start at 1. So the first thread has index 1, and the first block has index 1. So there's this -1 to compute this offset in blocks. For C folks, it's the usual C convention. Indexes start at 0 and count up to from 0. So the Fortran just needs to watch that minor adjustment. There's a couple more of these special variables which CUDA automatically provides for you. Grid dim, which will not generally be so interested in this course, is the total number of blocks in each dimension. Block dim is the number of threads per block in each direction. And then unique for each block is the block index and the thread index. The thread index being unique to each thread, I should say. And likewise in Fortran. Okay, so that's a one-dimensional problem. One could then naturally think about a two-dimensional problem. For example, if we had a matrix or an image, we might have some arrays declared in a two-dimensional fashion. Here I've got A, B, and C. This kernel is concerned with. So here C is supposed to be the element-wise sum of A and B. So to perform this operation for every element in that two-dimensional array, it is natural to describe that in a two-dimensional Cartesian picture, where I've made use of this not only this threaded index.x, but also thread index.y, and likewise for the block quantities. So in the kernel, I identify where I am in the x direction in this two-dimensional problem by a block index.x and thread index.x, and likewise the y picture uses the y component of this dim3 structure. You may, some people may be slightly surprised to see that I've used J as the variable associated with the x direction and I with the variable associated with the y direction. There is actually a reason for this, which we will come on to this afternoon. That's not just an accident. So at the execution side on the host, we need to declare two of these variables. These are just variables which we declare. We can have any old name we want, really. So I've here declared threads per block to be 16 by 16 by 1 in 3 dimensions. And then if we wish to cover the whole problem space, I need to allocate a number of blocks, which is n over 16 in each direction. Again, this is assuming that n is evenly divided by 16 without remainder. In practice, what one typically does is to make a decision about the number of threads per block, and there are various reasons for why one might choose a particular number, but if the total number of threads per block is something like 128 or 256, you probably won't go far wrong. Given that choice, it's then usually just a question of setting the number of blocks so that you have enough blocks to cover the whole problem space. Okay, so that's broadly the business of how one writes a kernel. So one is looking to split up the problem and execute individual parts in this threaded model where we're using these special variables to identify where we are in the problem space. And then we launch our kernel onto the device with this funny triple angle bracket execution configuration. Standard C programmers will, of course, note this triple angle bracket thing is completely non-standard. It's a CUDA extension. There are slightly more standard-looking ways of launching a kernel if one is interested. So another important point to realize about starting a kernel or launching a kernel is that execution on the device is going to be asynchronous. So if we're on the host and we start a kernel, we need to know when it is safe to ask, can we have the results back? And this is done through this CUDA API called CUDA device synchronize. So if that returns, this synchronizes us with the device, and we know that that kernel has finished execution. So it should always have in the back of your mind for CUDA that operations on the device and on the host are potentially asynchronous, and you may want to start worrying about, are you sure that something has completed before going on to doing the next thing. So you will see in the CUDA interface a lot of CUDA API calls have async at the end, which is signaling that this is an asynchronous operation. Okay, so those are broadly kernels, how one can write a piece of code and execute it on the device. The other thing we haven't really, sorry, this is just that point of synchronization. Again, we'll come on to say a bit more about synchronization later. But the other thing we need to think about is memory. So we're going to remember that I said at the start that the host, the CPU, and the device, the GPU, have these separate memory address spaces. So data accessed by the kernel, that is by the GPU, must live in the device memory. So for the purposes of this talk, we are going to manage this absolutely explicitly so that we understand what is happening here. Okay, so in C, device memory may be allocated to be associated with a standard C pointer by this CUDA API called CUDA malloc. So this CUDA malloc is asking that we allocate a certain number of bytes in device memory, which is this variable data. And then typically one just does CUDA free is the analogous call to release resources when you've finished using them. So the important thing to realize about a pointer so allocated is that that pointer, because it is in device memory, cannot be dereferenced in host code. So that's often can be a source of errors, which historically just gave you segv, but CUDA now prints a rather more friendly message to tell you you're trying to access device memory from the host. So if you think back to that picture we had at the start, I said we have to worry about moving data between the host and device. One does this explicitly using this CUDA memcopy function. It takes 4 arguments. The first 2 arguments are the destination, which in this case is the device pointer, the device reference, and there needs to be a host pointer, a host reference here. I'm going to say I want to copy this number of bytes, and then there is this special argument CUDA memcopy host to device, which is telling CUDA memcopy which way the transfer is to occur. So if one was going in the other direction, i.e. one wanted to copy device memory contents back to the host, you'd use CUDA memcopy. So the destination is now the host and the source is the device pointer, a certain number of bytes, and we have this special value CUDA memcopy device to host, indicating the direction. So in general, this is the API call. There are a couple of other acceptable values of this CUDA memcopy kind things, which include, for example, CUDA memcopy host to host and CUDA memcopy device to device, if you wanted to make such copies. Okay, so so that's the C picture. We explicitly allocate and move memory via these CUDA API calls. In Fortran, the situation is a bit different because arrays essentially in Fortran have some knowledge about themselves. One can actually use the compiler to help you in this process. So if one wants to make an allocation in device memory, we have this special CUDA Fortran extension which appears as an attribute in the declaration device there. So if we allocate against this data device variable, that allocation is in device memory via a standard Fortran allocate statement. And again, to release that device memory, just deallocate. So those are a bit like, you can even try using the CUDA API if you like. So the issue of copies is because the compiler now knows a given array is associated with either host or device, a copy can now be merely by examining the left and right hand side of an assignment. So if we made an array assignment data device equals data host, that is actually a copy of host data to device memory and back again. So in CUDA Fortran, there's no need for this explicit CUDA memcopy, although the sort of risk here is that you forget assignment is actually host to device copy, I suppose. Okay, so those are the two basic parts of the recipe we need to write a CUDA program. We need a kernel to execute code on the device, and we need to think about some memory management in terms of how do we obtain memory on the device, and how do we move memory back and forth between host and device. So we can now think about, as we go forward, to look at our first exercise. So a CUDA C code, which conventionally has had the extension .cu, may be compiled with the NVCC, the NVIDIA CUDA compiler, to give an executable which will run, start on the host and run the kernel on the device. if you're in CUDA Fortran, traditionally you would call your CUDA Fortran file with CUDA Fortran extensions a .cuf or a .cuf file, and such a file would be compiled. Previously, we've used the Portland Group compiler PGF90. As Portland Group have now been taken over by NVIDIA, this has been reborn as NV Fortran. So I'm going to, in the exercises, you'll be encouraged to use NV Fortran if you're in Fortran land. Okay, so that's just a summary. So we've got for C and CUDA Fortran, we have this API plus some language extensions which allow us to do memory management and kernel execution. So it should be said that CUDA has a very large API, and I've only talked about a very small subset, but one can make significant progress with that small subset. So CUDA is still evolving. This slide is slightly out of date. We should be up to CUDA 11 by now, and we have about one release a year, and some changes are still occurring. But at that point, we should be now ready to think about trying our first exercise. So at this point, we need to think about logging in to Cirrus and downloading the contents of the Git repository and finding the appropriate exercises. Okay, so I should now go away and check nobody is still waiting for an account, and we'll see how this goes. I think have a go, and if there's problems, we'll write them into the chat and we'll try and sort them out from there. Are there any questions arising from that stuff?
I did raise my hand, Kevin. Can you see that? Anyway.
Slightly, yes. Okay, got you. Yeah.
All right. I mean, I'm struggling with the exercise, but I'll get to that when we do that. But I just comment on your reveal.js slide there, that last exercise slide. It doesn't fit in a script.
It's just gone off the end, has it?
Yeah, I don't know why revealed. That's completely separate to the lecture, though. But it's just how to resize the whole Chrome browser to see what was beyond that, because I was worried there was stuff missing beyond it.
Yeah, that's probably my error, I think.
Anyway, okay. But I think it's online after that, the submit script.
Yeah.
I was just wondering about how you choose the number of blocks.
Yeah, okay. As I say, operationally, what one typically does is to actually choose the number of threads per block.
Yep.
So there are certain limits here which one cannot exceed. That is, one cannot exceed 1024 threads per block ever.
Okay, good.
And there are for many problems, it's a good starting point to choose 128 or 256 threads per block in total. The question then becomes, how many blocks do I need to cover the whole problem space? And it is the size of the problem space which will then determine the number of blocks at a given number of threads per block.
And so that won't change if you've got a Pascal or a different type of GPU card. Because
no, I mean this is determined. Well, okay, so the choice of threads per block might conceivably change depending on the hardware, but in practice don't do much. And your problem size is whatever it is. So those two things will fix the choices.
I guess
I'll
with
say
it
a bit more.
Embarrassingly parallel, it doesn't matter that it's processing those blocks. If it's more blocks than the number of GPU SMP things.
Yeah, so this is the abstract. You don't want to care about how many exactly what's in the hardware. You just want to set off as much work as possible and then let the GPU runtime sort it out.
Yeah. Okay.
Because as I said in the first talk, the key is supplying lots and lots of work. So if one bit of work gets stuck waiting for data, we can try and swap in something else to do something useful. This is the name of the game. So you need a nice big problem size with lots of blocks.
Right. Yeah. Thank you.
Any so if you want, there's a question in the chat about which module. So if you want to do, so for each exercise, there's a C template and a Fortran template. If you want to do the C, you're going to need NVCC, and you need to load the NVIDIA CUDA 10.12. If you want to do the Fortran, you need to do something slightly different, and you want the NVIDIA compilers module. A slightly annoying difference. If you want to do both, then you'll have to start thinking about swapping modules around as you go on.